Friends, welcome to the tutorial series on network analysis made simple. During the previous tutorial on classical approach to transient analysis, we learned the basics of transients, its causes and effects. Further, we learned the formation of differential equations for some circuits. We represented the standard form of representation of first order ODE and developed the procedure to solve it using classical approach. In fact, I feel that the previous tutorial is a prerequisite to proceed further. During this tutorial titled Step Response to RL and RC Circuits, we shall learn to apply what we have learned in the previous tutorial. Friends, during this tutorial, we shall find the complete solution of the system response at t is equal to greater than or equal to 0. We also study the behavior of inductance and capacitance elements at t is equal to 0 plus and at t is equal to infinity. This will help to find the integration constant while finding the complete solution. Friends, I am sure you will enjoy this tutorial. Friends, let us take an RL series circuit connected across a DC source in series with a switch K as shown in figure. Let's find the current in the circuit I of t, current in the inductance IL of t, and voltage across the inductance VL of t for t greater than or equal to 0 using classical approach. Before we proceed, I will introduce a few symbolic representations and their meaning. First, let us consider the time axis. We divide the time axis into four instances. One is t is equal to 0 and another is t is equal to infinity. With respect to t is equal to 0, we define t is equal to 0 plus, which is the time very close to t is equal to 0 as shown. Similarly, we define t is equal to 0 minus, which is very close to t is equal to 0 on the other side. I suggest you keep this in mind, it will be helpful. Next, consider a switch symbol. This is a normally open switch. When we say that it is closed at t is equal to 0, it has two meanings. One, at t is equal to 0 minus, the switch is open and it is open for an infinite time before closing. Another, at t is equal to 0 plus, it is closed and remains closed for infinite time unless otherwise it is operated again. Similarly, this switch is a normally closed switch and it is open at t is equal to 0. At t is equal to 0 plus, the switch is open and remains open for infinite time. At t is equal to 0 minus, it is closed and remains closed for infinite time on the other side. Next, consider a step input. Figure shows the step input. Mathematically, we can represent it as v of t is equal to 0 for t less than 0 and it is equal to v for t greater than 0. Hope these basics are clear to you. Friends, next consider the circuit for t greater than or equal to 0. The equation for the system response can be written as R into I plus L into di by dt is equal to V. Let it be equation 1. After dividing throughout by L, we get equation 2, which is the standard form of the first order ODE. By comparing equation 2 and 3, we get P is equal to R by L and Q is equal to V by L. We know that the solution of first order ODE is equation 4. By substituting the values of P and Q, we get I of t is equal to e to the power of minus r by L into t into V by L into integration e to the power of r by L into t dt plus k into e to the power of minus r by L into t, let it be equation 5. By solving the integration term, we get I of t is equal to V by r plus k into e to the power of minus r by L into t, let it be equation 6. Now, Using the knowledge of electrical engineering, let us find I of 0. Consider the circuit at t is equal to 0 minus the switch K is open. Hence, I of 0 is equal to 0 and IL of 0 is 0. Since the inductance opposes the change in current, IL 0 plus also is equal to 0. We know that I of 0 at time t is equal to 0 is 0. Substituting these values in the equation of I of t, we get k is equal to minus v by r. Now, by substituting the value of k in the equation 6, we get I of t is equal to v by r minus v by r into e to the power of minus r by l into t, or I of t is equal to v by r into bracket 1 minus e to the power of minus r by l into t, let it be equation 7. This equation is the complete solution for I of t. Since L and R are in series, IL of t also is equal to V by R into bracket 1 minus e to the power of minus R by L into t, let it be equation 8. Now, to know the behavior of inductance at t is equal to 0 and at t is equal to infinity, we need to find VL. We know that VL of t is equal to V minus VR. By substituting for Vr is equal to I into R and the value of I and simplifying it, we get Vl of t is equal to V into e to the power of minus R by L into t, let it be equation 9. By representing IL and VL graphically, we get the graph shown in figure. Observe that at t is equal to 0, IL of 0 is 0 and VL of 0 is equal to V. What does it mean? It means that a zero current and a finite voltage imply open circuit. Therefore, if the inductance is switched across a step input at t is equal to 0 and initial current through it IL of 0 is 0, then at t is equal to 0 plus inductance behaves as open circuit. Similarly, if we observe at t is equal to infinity, we see that VL of infinity is equal to 0 and IL of infinity is equal to V by R, meaning a zero voltage and a finite current imply short circuit. Hence, if the inductance is switched across a step input at t is equal to 0 and initial current I of 0 is 0, then at t is equal to infinity, inductance behaves as a short circuit. On the other hand, if there is an initial current flowing through the inductance is I naught before switching, then it acts as a current source as shown both at t is equal to 0 and at t is equal to infinity. Hope you have understood this. Friends, if you have understood the behavior of inductance at t is equal to 0 and at t is equal to infinity, it will be very easy to obtain the behavior of capacitance. Consider an RC series circuit connected across a step input as shown in figure. After the switch K is closed at t is equal to 0, the system response for t greater than or equal to 0 can be represented by an equation R into I plus 1 upon C into integration I dt is equal to V. Let it be equation 1. You see that this equation has turned out to be an integral-differential equation. Hence, by differentiating it, we get R into di by dt plus I by C is equal to 0. Let it be equation 2. 0 because phi is constant after t is equal to or greater than 0. Note that. By dividing throughout by r, we get di by dt plus 1 by rc into I is equal to 0. Let it be equation 3. This is similar to the standard form of first order ODE equation 4. Comparing equation 3 and 4, we get P is equal to 1 divided by R into C and Q is equal to 0. Also, we know that the solution for the first order ODE is I of t is equal to e to the power of minus pt into q into integration e to the power of pt dt plus k into e to the power of minus pt. Let it be equation 5. Since q is 0, we get I of t is equal to k into e to the power of minus pt. Let it be equation 6. By substituting the value of p equal to 1 by rc, we get I of t is equal to k into e to the power of minus 1 by rc into t. Let it be equation 7. Now, using the knowledge domain of networks to find k, we need to find I of 0. Before that, we have to find Vc 0 minus if present. For that, consider the circuit at t is equal to 0 minus. We know that the switch K is open, voltage V is not applied to the circuit, so the capacitor is not charged. Hence, Vc 0 minus is equal to 0. Friends, I will tell you another easiest way of finding Vc0 minus. There is only one source V in the circuit. Trace from the negative terminal of the source V, you see that it is connected to one terminal of the capacitor. Yes. Now, trace from the positive terminal of the source V, you see that it terminates at the switch K itself and K is open. So, it does not reach the capacitor terminal at all. So, the capacitor is uncharged. Is it not simple? So, friends, we know that the capacitor opposes the change in voltage. So, Vc 0 minus is equal to Vc 0 plus. Therefore, Vc 0 plus is equal to 0. Friends, it is not enough if we find Vc0 plus only, but what we want is I of 0. So, consider the circuit for t greater than or equal to 0 as shown in figure. The switch K is closed, voltage V is applied, but Vc0 plus is 0. That you know. What does this mean? Friends, the entire voltage V appears across R at t is equal to 0 plus. That is the beauty of it. Therefore, I of 0 is equal to V by R amperes. So, I of 0 at t is equal to 0 is V by R amperes. Now, consider the equation for I of t as obtained earlier. By substituting I of 0 is equal to V by R and t is equal to 0 in equation 7, we get k is equal to V by R. This value of k, if we substitute in equation 7, we get the complete solution for I of t as I of t is equal to V by R into e to the power of minus 1 divided by RC into T. Let it be equation 8. Since R and C are in series, IC of T also is equal to V by R into e to the power of minus 1 by RC into T. Let it be equation 9. To obtain the behavior of capacitance at t is equal to 0 and at t is equal to infinity, we need to find Vc of t for t greater than or equal to 0. We know that Vc of t is equal to V minus Vr. So, by substituting for I of t and solving it, we get Vc of t is equal to V into bracket 1 minus e to the power of minus 1 by Rc into t. By drawing the graph of IC and VC as shown in figure, we find that at t is equal to 0, I of 0 is equal to V by R amperes and VC 0 is equal to 0. We know that a zero voltage and a finite current imply short circuit. So, if the capacitor is switched across a step input at t is equal to 0 and if VC 0 plus is 0, then the capacitor will behave as a short circuit at t is equal to 0 plus. Similarly, at t is equal to infinity, we observe that Vc infinity is equal to V and Ic infinity is equal to 0. So, a zero current and a finite voltage imply open circuit. So, at t is equal to infinity, capacitor behaves as open circuit as shown. Now, if there is initial voltage, say Vc0 across the capacitor is present before switching, then it will behave as a voltage source of Vc0 as shown. Is it not simple, friends? Friends, let me summarize about what we have learned till now. If the initial current through the inductance before switching I naught equal to 0, and if it is switched across a step input at t is equal to 0, at t is equal to 0 plus, it will behave as open circuit, and at t is equal to infinity, it will behave as a short circuit. Similarly, if the initial current through the inductance before switching is I naught and is present, then at t is equal to 0 plus and at t is equal to infinity, it will behave as a current source of I naught amperes as shown. On the other hand, if the initial voltage across the capacitor Vc0 is equal to 0 before switching, and if it is switched across a step input at t is equal to 0, at t is equal to 0 plus, it will behave as a short circuit, and at t is equal to infinity, it will behave as an open circuit. If initial voltage Vc0 is present, then it will behave as a voltage source of Vc0 both at t is equal to 0 and at t is equal to infinity. Remember these facts as we are going to use these while solving the numerical examples.
Friends, to emphasize the concepts we have learned, let us take an example to find the complete solution for I of t, IL of t, VR of t and VL of t for t greater than or equal to 0 in the circuit shown in figure. After the switch K is closed, by writing the equation for the system response, we get 30 into I plus 15 into di by dt is equal to 60. By dividing throughout by 15 to bring the equation to the standard form, we get di by dt plus 2I is equal to 4. Let it be equation 2. By comparing this equation with the standard form of first order ODE, we get P is equal to 2 and Q is equal to 4. But we know the solution for the first order ODE is equation 3. By substituting the values of P and Q, we get I of t is equal to e to the power of minus 2t into 4 into integration e to the power of 2t dt plus k into e to the power of minus 2t. By solving the integration term, we get I of t is equal to 2 plus k into e to the power of minus 2t. Let it be equation 4. To find k, we should find I of 0 at t is equal to 0. Consider the circuit shown in figure for t is equal to 0 minus. At 0 minus, k is open and it is open for infinite time, hence inductance will behave as though it is at t is equal to infinity. So, at t is equal to 0 minus, L is short and k is open, hence I0 minus is equal to 0, so I0 plus also is equal to 0. By substituting this value in equation 4, we get k is equal to minus 2. Therefore, equation 4 can be written as I of t is equal to 2 into bracket 1 minus e to the power of minus 2t, let it be equation 5, and this is the complete solution for I of t. Since R and L are in series, IL of t is equal to 2 into bracket 1 minus e to the power of minus 2t. Let it be equation 6. We know VR of t is equal to I into R, and by substituting we get VR of t is equal to 60 into bracket 1 minus e to the power of minus 2t volts. Similarly, we know that VL of t is equal to L into di by dt. By substituting and differentiating, we get VL of t is equal to 60 into e to the power of minus 2t volts. Friends, is it not simple? Friends, next we shall take up an RC series circuit connected across a step input as shown in figure and find the complete solution for I of t, VR of t and Vc of t for t greater than or equal to 0. By writing the equation for the system response, we get R into I plus 1 upon C into integration I dt is equal to V. let it be equation 1. By substituting the values, we get 10 into I plus 1 divided by 0.1 into integration I dt is equal to 20, let it be equation 2. By dividing throughout by 10 and differentiating it and bringing it to the standard form of first order ODE, we get dI by dt plus I is equal to 0, let it be equation 3. By comparing with the standard format of first order ODE, we get P is equal to 1 and Q is equal to 0. We know the solution for the first order ODE is equation 5. Since Q is 0 and P is 1, we get I of t is equal to K into e to the power of minus t, let it be equation 6. Now, we have to find K, for which we need I of 0 at a time t is equal to 0. But at a time t is equal to 0 minus, we know that the switch K is open and it has remained open for infinite time. So, at t is equal to 0 minus, capacitor will behave as though it is at t is equal to infinity and hence it is open. Therefore, at t is equal to 0 minus, K is open and C is open. So, Vc0 minus is equal to 0. We also know that the capacitor opposes the change in voltage, hence Vc0 plus also is equal to 0. Now, to find I of 0, consider the equivalent circuit at t is equal to 0 plus. At t is equal to 0 plus, switch K is closed, capacitor C is short, but Vc0 plus is equal to 0. So, I of 0 is equal to 20 divided by 10, which will give us 2 amperes. Now, by substituting I of 0 is equal to 2 ampere at time t is equal to 0 in equation 6, we get K is equal to 2. Putting this value of K in equation 6, we get I of t is equal to 2 into e to the power of minus t, let it be equation 7, and this is the complete solution for I of t. We know that VR is equal to I into R, and hence substituting the values, we get VR is equal to 20 into e to the power of minus t volts. Similarly, Vc is equal to V minus VR, and by substituting the values and solving, we get Vc is equal to 20 into bracket 1 minus e to the power of minus t volts. Friends, is it not simple? Friends, now let us consider another interesting example to find equation for I of t and VL of t for t greater than or equal to 0 in the circuit shown in figure. The switch K is closed at t is equal to 0. Also, it is given that the circuit is in steady state before switching. Friends, note that at t is equal to 0, the switch K is closed. So, current source of 5 ampere is short circuited and its value becomes 0. By writing the system equation for time t greater than or equal to 0, we get R into I plus L into di by dt is equal to 0. Let it be equation 1. By substituting the values, we get 40 into I plus 20 into 10 to the power of minus 3 into di by dt is equal to 0. By rearranging it in the standard form, we get di by dt plus 2000 I is equal to 0. Let it be equation 2. By comparing it to the standard form of first order ODE, we get P is equal to 2000 and Q is equal to 0. But we know the solution for the first order ODE is equation 4. Since Q is equal to 0 and P is equal to 2000, by substituting and solving it, we get I of t is equal to K into e to the power of minus 2000 t, let it be equation 6. Now, using the initial conditions, we have to find the value of K. We know that at t is equal to 0 minus, the switch K is open, and by drawing the circuit at t is equal to 0 minus, we can easily see that IL0 minus is 5 amperes. Hence, IL0 plus also is equal to 5 amperes, and hence I0 is equal to 5 amperes at a time t is equal to 0. Substituting I0 is equal to 5 ampere at time t is equal to 0 in equation 6, we get K is equal to 5. By substituting this value of k in equation 6, we get I of t is equal to 5 into e to the power of minus 2000 t, let it be equation 7, and this is the complete solution for I of t. To find VL of t, we know that VL is equal to L into di by dt. By substituting the values and solving it, we get VL is equal to minus 200 into bracket e to the power of minus 2000 t volts. Friends, here is another different circuit to find Vc of t for t greater than or equal to 0. This is given that the switch is closed at t is equal to 0. The circuit is in steady state before switching. It also is given that initial condition is 0. What does this mean? We find that there is one energy storing element, capacitance, in the network. So, the meaning of initial condition being 0 given is Vc0 is equal to 0. This you have to note. This has reduced our burden to a little extent. We are now required to find Vc of t for t greater than or equal to 0. So, by writing the circuit for t greater than or equal to 0, we get to the circuit shown in figure. You find that the switch K is closed. Friends, we want Vc of t. You find that this Vc of t is the voltage of node 1. So, by writing the nodal equation for node 1, we get Vc minus 10 divided by 3 plus Vc by 2 plus C into dVc by dt is equal to 0. Let it be equation 1. By taking LCM 6 and solving and bringing the equation in the standard form of first order ODE, we get dVc by dt plus Vc is equal to 4. Let it be equation 2. By comparing this equation with the standard form of ODE equation 3, we get P is equal to 1 and Q is equal to 4. Also, we know the solution for the first order ODE is equation 4. By substituting the values of P and Q and solving it, we get Vc of t is equal to 4 plus k into e to the power of minus t. Let it be equation 6. It is given that Vc0 is equal to 0 at time t is equal to 0. So, substituting this value in equation 6, we get k is equal to minus 4. Substituting the value of k in equation 6, we get Vc of t is equal to 4 into bracket 1 minus e to the power of minus t, and this is the complete solution for Vc of t. Therefore, Vc at 1 second is equal to 4 into bracket 1 minus e to the power of minus 1, which will give us Vc at 1 second is equal to 2.528 volts. So friends, in the problem, note that we wrote Kirchhoff's current equation for node 1. Like this, we have to use proper technique depending on what we are asked for to find. Friends, here is yet another different problem shown in figure. It is given that the circuit is in steady state while the switch K is in position A. Also, it is given that the switch K is changed over to position B at t is equal to 0. We are required to find I of t for t greater than or equal to 0. First, let us find the initial current through the inductance if present at t is equal to 0 minus. We know that at t is equal to 0 minus, the switch K is in position A and the circuit is in steady state, meaning the switch is in position A for infinite time before changing over, and hence inductance will behave as though it is at t is equal to infinity and it is short. Therefore, I of 0 minus is equal to 10 divided by 5, which give us 2 amperes. Hence, IL0 minus is equal to 2 amperes and IL0 plus also is equal to 2 amperes. Now, we move to the next status for t greater than or equal to 0. The switch K is changed over to position B at t is equal to 0. For t greater than or equal to 0, the system equation can be written as r into I plus L into di by dt is equal to V. Let it be equation 1. By substituting the values of R, L and V and rearranging the equation in the standard form of ODE, we get di by dt plus I is equal to 3. Let it be equation 2. By comparing this equation 2 with the standard form, we get P is equal to 1 and Q is equal to 3. We know that the solution of first order ODE is equation 4. By substituting the values of P and Q and solving the integration term, we get I of t is equal to 3 plus k into e to the power of minus t. Let it be equation 6. But we know that I of 0 is equal to 2 amperes at time t is equal to 0. Hence, by substituting these values in equation 6, we get k is equal to minus 1. Therefore, by putting this value of k in equation 6, we get I of t is equal to 3 minus e to the power of minus t. Let it be equation 7, and this is the complete solution for I of t. Friends, I am sure by going through this tutorial, you might have felt that the classical approach of solving for transients is so easy compared to transform methods or by applying pure mathematical approach. Hope you have enjoyed this tutorial. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.